Today, I'm going to present the efficient variance estimator of AUC and its applications to binary classification. This is joint work with my former thesis student, Alex Guo from Wellesley College, where paper was published in Statistics Medicine earlier this year. To find more information about the proposal and the detailed algorithm, you can refer to the paper where the information is shared below right here. So here is the outline of my presentation today. I'll start with a brief introduction of binary classification problem, and then we'll focus on the evaluation method using the ROC curve, and then calculate the AUC score. In practice, there are several different ways to approximate the AUC score, but here we consider the use statistic estimate of AUC. And after that, we propose unbiased variance estimator of AUC, in order to consider the sampling variation of the AUC score in order to select the truly optimal model. In addition, we also consider an efficient realization of a proposed variance estimator of AUC. In the end, I'll present some simulation results and a real data example. Binary classification is the task of answering whether or not an experimental unit, such as a patient, belongs to the category of interest or not. It has many different applications in various disciplines. In addition, we have several available approaches to solve a binary classification problem. For instance, one may consider fitting a generalized linear regression model, such as logistic regression or probability regression. Or we may consider Bayesian approach using a Bayes classifier or conduct linear or quadratic discriminant analysis. Furthermore, there are also machine learning types of methods, including support vector machines, random forest, or bagging. Here I have a simple graphical illustration of a linear binary classifier. And this is the data set that we'll revisit at the end of today's talk. The response of interest is whether the patient has heart disease or not. So we have the two responses, yes or no. And then this graph is drawn over the top two principal components of the higher dimensional feature space. The linear binary classifier is trying to separate the diseased patients from the patients that are free of disease. So here we use the blue points represents the patient with disease and red points to represent the patient without disease. However, as we can imagine, all of those binary classification methods are not perfect, right? So clearly we do have some mismatch. So some of the patients with disease are misclassified into the no disease group and vice versa. And that's why we often need to evaluate how well a binary classifier can fit like a test data set. Especially this is important when it comes to variable selection or model comparison across the different available binary classifiers. Our later proposal applies any binary classification method. However, for ease of notations and illustration, so I'm going to focus on logistic regression as an example. And here I'm going to present some notations that we are going to refer to the following of the talk. We denote y sub I as the ith response. It is equal to 1 if the ith unit falls into the category of interest, and we label it as a positive group. Otherwise, yi is equal to 0, and this is our negative group. Pi sub I is the probability that the ith unit falls into the category of interest. The logistic regression model assumes that on the logit scale, or say the log-odd scale, we have a linear combination of p different predictor variables. Equivalently, the model can also be expressed in terms of the probability of interest. So this is a nonlinear function, exponential function over 1 plus exponential function, where the exponent is a linear combination of the p different predictors. Once we have our logistic regression model, we can use some method such as maximum likelihood algorithm to estimate unknown beta coefficients in order to obtain the fitted model that yields a predicted probability pi hat. In the end, one may compare pi hat with a discriminating threshold denoted by C in order to decontaminate pat hat into a binary outcome, either zeros or ones, so that we know ultimately whether we are going to predict a test observation to be either positive or negative. Here I have summarized the flow for the entire problem-solving process. We start with a binary classification problem, and then we may consider different binary classifiers to answer and address this question. And this can be any of the binary classification method I summarized in the earlier slide, or it can also be one particular method, but we consider using different number of predictors in the model. Regardless, often we have a set of candidate models under comparison. In order to choose which one is truly optimal, we need to calculate some performance evaluation metrics, and such as the AUC scores. However, the AUC score is a sample estimate, and that is data dependent. In other words, given the current data set, the model with the highest AUC score is not necessarily truly optimal. If we change to another data set independently taken from the same target population, we still fit the same set of candidate models, it is likely that the model with the highest AUC score may change. That's why in practice, it's very important for us to evaluate the variation of AUC estimate. So here it involves our proposal of this paper or the talk, which is a variance estimation of AUC score. So after we have the AUC variance estimator, and then we can accomplish model selection with consideration of AUC variation so that we can choose the truly optimal model. So now we have had our fitted model, such as the fitted logistic regression model, and then say we may have several different set of predictor variables that we want to plug into these models. We have several different potentially candidate models to compare. And then we can calculate some performance metrics to evaluate which one is better than the others. Here are some summarized commonly used performance metrics, including accuracy, precision, sensitivity, which is also called true positive rate, specificity, which is also referred to as a true negative rate. Basically, once we have our fitted probability, or say our fitted logistic regression model, and we can compare the predicted probability with the discriminating threshold in order to get the counts, like the true positive counts, false positive, true negative, and false negatives in order to calculate all of these performance metrics. However, one thing to note here is that the values of all of these performance metrics depend on the discriminating threshold C. When we alter C, these measures also change accordingly. The very natural question is whether there is any tool to evaluate the performance of binary classifier by considering various values of the discriminating threshold C. Well, the answer is yes, and such a tool is our ROC curve, receiver operating characteristic curve. An ROC curve is the plot of the true positive rate sensitivity against the false positive rate, defined as 1 minus the specificity. It is drawn of a binary classifier across the different discriminating threshold values. So here, let's consider like more formal definition of the ROC curve. So let x plus and x minus be the vectors of observed features from the positive class and negative class respectively. The true positive rate sensitivity is a function of the discriminating threshold C. Given a logistic regression model, for instance, this function can be written as the probability or say conditional probability of the predicted probability per hat of observation taken from the positive class being greater than the threshold C, given the true class is 1. Similarly, the false positive rate is a function of discriminating threshold C. It is the conditional probability that per hat of observation randomly taken from the negative group have a value greater than C, given that the true label of this observation is equal to 0. An ROC curve plots the true positive rate against the false positive rate by varying the discrimination threshold C between 0 and 1. In practice, the area under our curve, AUC, is often used as a measure to evaluate the performance of a binary classifier. And it is well known that AUC takes value between 0 and 1, and the higher value in AUC indicates better performance of the binary classifier. As a benchmark, random guessing yields AUC equal to 1/2, 50%. In general, we hope that at least our binary classifier can be much better than random guessing. So we hope that the score AUC would be higher, or say much higher than 0.5. AUC actually has a very interesting probabilistic interpretation. It can be written as the following conditional probability. So here we'll randomly take observation from the positive class and observation from the negative class. AUC represents the probability that a randomly taken positive unit is ranked higher than a randomly taken negative unit. Here, ranked higher means having a higher predictive probability in the context of generalized linear regression, or in other contexts, such as using a support vector classifier. This may mean that having a shorter perpendicular distance to the decision boundary. In practice, AUC can be estimated using different methods given a data set, such as normal approximation, kernel smoothing, or U-statistics. In this talk, we focus on the U-statistic estimate of AUC. For ease of notations, let's consider pi hat as the classification method under evaluation. It can be the fitted logistic regression model. Based on the probabilistic expression of AUC, it is the probability of pi hat of x plus greater than pi hat of x minus. We know that this can be equivalently written as expectation of an indicator function. And furthermore, we can express all these expectations. So this can be written as a double integral of the indicator function multiplied by the two probability density functions of the positive observation and negative observation respectively. From this expression, it's easy to see that AUC is a regular statistical functional of degree 2. And as a result, there exists unbiased estimator of AUC in the form of a two-sample U-statistic. Next, we are going to construct the U-statistic estimate of AUC. Before, let's have a quick recap for the definition of a two-sample U-statistic. Consider two independent samples of different sizes, N1 and N2, where N is the total sample size, N1 plus N2. So you can imagine these two independent samples can be or sample of the patients with positive labels and sample of patients with negative labels. We denote these two independent samples using notation X and Y, respectively. In general, a two-sample U-statistic of degree k, where k is equal to k1 plus k2, is given by the following expression. So here we calculate the kernel function phi by plugging into k1 components from the first sample and k2 components from the second sample. And then we average over all the possibilities. So we consider all the possible combinations of N1 choose k1 and N2 choose k2. In general, phi is assumed to be a symmetric function that is a permutation invariant over the indices within each independent sample. When you look at the definition of a two-sample U-statistic, it may seem a little bit complicated. However, in the next slide, you're going to realize that in the context of AUC estimate, it's actually pretty simple. Given ID sample of size n, we denote the number of observations with true positive labels as n1 and the number of observations with true negative labels as n2. Okay. Then, because of the expression of the AUC in terms of a probability or say a statistical function of degree 2, we can construct unbiased estimator for AUC in the form of the following U-statistic. It is a two-sample U-statistic, as we have the positive sample and negative sample. But here, the kernel function phi actually only has two components. We only need to take one observation from the positive sample and one observation from the negative sample, and then we average over all the possibilities. Furthermore, the kernel function in this context is pretty simple. It is an indicator function. Okay, so the indicator of comparing whether pair hat of x plus is greater than pair hat of x minus. Because the AUC is a statistical function of degree 2, and the degree of the constructed U statistic U sub AUC is also equal to 2. And furthermore, it is a common result and very easy to verify that the U statistic estimator of AUC is equivalent to the Mann Whitney statistic. In practice, given IID sample and a set of candidate binary classifiers, one may consider using AUC scores to compare the performance across the different classifiers, and then choosing the one with the highest and largest AUC score. However, as I briefly mentioned earlier, due to sampling variation, the model with the largest AUC estimate is not necessarily optimal. Therefore, it is crucial to evaluate the variance of AUC estimate. And this is the main focus of our research and our paper. In the following, we are going to propose unbiased variance estimator of AUC estimate. Our work was motivated by Wang and Lindsay in 2014, where they proposed unbiased variance estimator of a U statistic in the context of a one-sample scenario. We extend the result to a general K-sample U statistic, where K can be greater than or equal to 2. Because here in this talk, I focus on the illustration of AUC variance estimation, and the AUC estimate is a two-sample U statistic. So therefore, we are going to focus on the construction of the unbiased variance estimator of a two-sample U statistic. Although our result can be extended to a general K-sample U statistic that involves more than 2 independent samples. Sorry for the interruption. I didn't switch my slide correctly. So this idea of the construction for a proposal is based on this expression of the variance of a U statistic, or say the variance of any statistic. We know that in general, the variance of a statistic can be written as the expectation of the second moment minus the square of the expected value. If we aim for constructing an unbiased estimator for the U statistic, what we can do is we can find unbiased estimator for each of the two terms on the right-hand side. Okay. And clearly, the first term is very easy to be estimated unbiasedly. We can directly use UN squared, and that is already unbiased estimator for the first term, because the expected value of UN squared is already the first term. And the difficulty is how we can construct an unbiased estimator for the second term. That is the squared of the expectation. So here is the theorem of our proposal. Given a two-sample U statistic, its unbiased variance estimator can be written as Q of K minus Q of naught. And we denote our proposed variance estimator as V hat sub U, where the subscript U stands for unbiased. In general, Q of C is defined as follows. So here we consider two different kernel functions, and then we only calculate their product whenever the number of overlaps between the two subsamples within the kernel functions is at most C. And then we average over all the possible product terms. Here, P sub C is a set containing all of the subsamples of size K, where the number of overlaps between these two subsamples at most C. And then N sub C represents the number of pairs of such subsamples within the set P sub C. It's easy to see that if we set this value C to be K, which is the degree of our U statistic, then basically it means that we consider the product between two kernel functions where they can have at most little K overlaps. Well, each kernel function has little k components. So if we consider two kernel functions with at most little k overlaps, that means we can consider all possible pairs of such subsamples. And that eventually gives us the value un squared. In other words, the first term in the definition, Q of k, is equal to un squared. And this is already the unbiased estimator for the first term of our true variance expression, the previous slide. And the second value, Q of naught, why it is unbiased for estimating the second term. Let's take a look. So here, if we take expectation of Q of naught, basically we are calculating expected value of the average of the product terms where the two subsamples have no overlaps at all. And expected value of the average can be written as expectation of the individual term. So the expectation of phi of the first subsample times phi of the second subsample. Because the two subsamples do not have any overlaps, they are independent. We have an ID sample, right? So then the expectation of the product can be written as the product of two individual expectations. And the expectation of each kernel function is the same value as the expectation of the U statistic. So that's why in the end, E of Q of naught is just equal to the square of the expectation of UN. Okay. So now we have both Q naught estimating the second term unbiasedly and QK estimating the first term unbiasedly. And we compute the difference between these two terms, we get unbiased estimator for the true variance of UN. In the case of AUC variance estimation, an expression is much simpler. The kernel function phi again is just an indicator function with two arguments. We get one component from the first sample, the positive class, and then one observation from the negative class. So V hat AUC represents or proposed unbiased variance estimator for the AUC score, where the AUC score is written as a two-sample U statistic form. And in this case, it is written as Q of 2 minus Q of naught, because our AUC score just have degree 2. That's why K is equal to 2 here. Furthermore, Q of 2 is just the square of our U statistic AUC estimate. And Q of naught is the average of the product between the two kernel functions, the two indicator functions, where we have no overlaps. Okay. So here I have to correct my notation. I used to use as the probability, but here I change it to P. Sorry about that. So our proposed variance estimator has already been shown to be unbiased. Furthermore, we have an efficient realization of it. In general, the original formula may be computationally expensive, especially for the calculation of Q of naught, because we have to consider all the possible subsamples, pairs of subsamples that do not have any overlaps. So here we devise a partition resampling realization. And basically what we are trying to do is we are going to divide each given data set into M blocks, where M is the minimum number between N1 and 2. So in our case, and this is very easy to realize. And then we are going to take one element from sample 1 and then one element from sample 2. And we can follow the following equation to calculate or propose the variance estimator very efficiently. Due to time constraint, I'm not going to go through this algorithm in details, but I just want to point out that we do have an efficient realization with a partition resampling scheme, and which can help to calculate or propose variance estimator much faster than based on the original formula. So next, I want to spend the remaining couple minutes to talk about the simulation studies and the real data example. In the simulation study, we want to compare the performance of our proposed variance estimator with the commonly used resampling-based variance estimators, such as Bootstrap and Jackknife. And we simulated 1,000 independent data set, each of size 100 or 500. So we have two different options of the sample size. And to generate a binary response, we start with generating a continuous response based on the following linear relationship, where the random error epsilons come from a logistic distribution. And after we obtain the binary After we obtain the continuous response, we convert it into binary outcome by comparing y superscript c with a fixed threshold t. And we choose t carefully so that in each simulated data set, we have approximately 50-50, 40-60, 30-70, or 20-80 split between the positive and negative classes. So here I want to consider in different scenarios with different degrees of difficulties for the imbalanced data setting, and whether we have similar conclusions when it comes to the performance comparison. And the X random variables are each simulated independently from uniform distribution has been standardized. So as a result, the significance of the predictor variables actually are driven by the corresponding coefficient. In other words, if we consider, say, the best model with only one predictor variable, and that will be the one with X1. And the best model with two predictors will be with X1, X2. Also notice that the true coefficient in front of x6 is equal to 0. So x6 is actually a redundant predictor variable. Okay. And we have 6 models under consideration and comparison. The best model with only one predictor up to the full model with all 6 predictor variables. Again, model 5 is the true model form because the true coefficient in front of x6 is equal to 0. So for a given simulated data set and each of the 6 candidate models, we calculate the UCD estimate of AUC using the R package, ROCR. And then we realize our variance estimator for the AUC score under the partition resampling design, where we use the different number of partitions. So number of partitions taken to be 100, 1,000, or 10,000. For bootstrap and jackknife methods, we are going to use the 1,000 bootstrap and jackknife samples given a simulated data set. One thing to note here is due to the violation of the smoothing condition for the consistency of delete 1 jackknife, we implemented delete D jackknife, where D was set to be 10 when the sample size is 100 and 25 when N is equal to 500. So here I only present you the results. We have a 40-60 ratio between the positive and negative classes in the simulated data. And here what we compare is the mean square error value and multiply by a constant for the ease of visualization. And we have the horizontal axis represents the 6 candidate models. And then the left graph is when sample size is 100, the right one is sample size 500. Okay. And the conclusion here is, in general, our method or proposed unbiased variance estimator gives a very similar performance to the bootstrap variance estimator. The jackknife in general is the worst. Okay, and also by increasing our number of partitions, the performance of our proposal improves. When it comes to computational cost, you can see the vast improvement of our proposal. So here again, we have different sample sizes and different ratios between the positive and negative classes. And then I showed you the bootstrap, jackknife, and or unbiased method. Okay. So here I only show like 2 choices of number of partitions. What you can see is that even with the number of partitions equal to the number of bootstrap and jackknife samples used in the calculation of each variance estimator, our method can be 10 to 30 times faster than the bootstrap and jackknife methods. And given similar performance and much faster computational time, and clearly our proposal is really valuable in existing literature. In the very end, I'll quickly go through a real data example because I'm running out of time. You may have heard the timer I set up. So here we consider heart disease data sets that I briefly illustrated at the beginning using a graph. The response is whether the patient has heart disease or not. And the goal is to correctly and accurately predict the patient belonging to the heart disease group versus not. And we did a little bit trimming of the data set. We used a sample of 297 observations and 13 different predictor variables. And we consider 13 candidate models, where each model is the best one given a certain number of predictors. And we calculate the AUC score for each of the 13 models. It turns out that model 11 has the largest AUC score. In practice, if one doesn't care about sampling variation of AUC estimate, and people may just choose model 11 as the optimal model. However, when we look at the other AUC scores, there are several more parsimonious models whose observed AUC score are very close to maximum, indicating that a model with less complexity may yield comparable predictive power as model 11. So here we consider to employ the one standard error rule, where one selects the most parsimonious model whose AUC score is within one standard error of model 11. In order to implement this, we need to calculate the standard error of model 11's AUC score. So this can be realized by our proposed variance estimator. We take a square root of our variance estimator that gives us the standard error. We can also do this by bootstrap and jackknife methods. And here is the graph. The top two are the one standard error rule realization using our unbiased variance estimator, where the number of partitions is equal to 100 or 1000. And bottom two panels are estimating the standard error using either bootstrap or jackknife methods. The final conclusion is all of these different methods yield model 6 as the optimal one under the one standard error rule. So regardless of how we estimate the variance, we are going to select model 6 if we take into consideration of variation of AUC estimate. And together with our conclusion from simulation studies, we know that our proposal is much faster to calculate. It's 10 to 30 times faster to calculate. So therefore, our proposal should be preferred in practice in this context for model comparison when considering variation of AUC score. And that's all I want to share today. And thank you very much for your attention. And I'm sorry that I'm using almost all the 30 minutes. Hopefully I didn't run over time too much. And I also hope that you enjoy the rest of the conference, the other talks in this session.